Let's continue from where we had stopped. Let's take one example, and through the example, let's see what are we getting to. Okay, so what we have here is, let's take this number 0 0 1 0 0. Another number we'll take is 0 0 0 1 0, and the last one we'll take is 0 1 0 0 0. The component exponent would be 0 1 0 1 1 and 0 1 0. Now see, these are the examples given. So what you can do is you can just take up some time, pause it, and just solve this. Now when you solve, what are we getting at? If you look at all of them, right, what's the solution, what you're getting it? Now these are three typical floating point numbers. Okay, now what do they represent? Now if you look at all the numbers, uh, it's 2, so we are moving 1 2 here. Okay, and other one is 2 plus 1 3, so you move 1 2 3, and the last one is moving 1. Now if you look at all these numbers, what does it represent? They all represent number 1. Okay, so these all the three have the ternary value 3. Okay, in fact there are an infinite numbers of ways to represent the number 1 using floating point notations. However, the number of bits we can use for Mantissa and exponents will limit the number of possible combinations in a given format. Now the format what we are using here is, let's say, 5 plus 3. So the given, whatever is a given format, whether I'm using 12 plus 4 or 8 plus 4, so it will always have a limit for the possible combinations in a given format. In fact, we can represent in many different ways is a problem, right? So what need we need a consistent way of storing point binary. We need a consistent way of storing uh, the floating point binary number. So there is only one way of representing any given number. To this we call it to normalize the number, right? So what we have is a different ways of doing it. So we need to have a consistent way of storing it, right? Now, besides having a consistent way to represent numbers, another advantage of normalized floating point binary is the assurance we are storing numbers with the highest possible degree of accuracy. What are we looking at? Highest degree of accuracy. Okay, so whatever you're storing, we have a assurance that it gives that, okay, this number what is stored is the more accurate than the previous one, or the most accurate this is. So we call it as normalizing the number. To understand that this number is a normalized floating point binary, there are two things that you have to remember. First, all positive normalized numbers start with 0, 1. Second, all negative normalized numbers start with 1, 0. So always remember this important thing, that the positive numbers will start with 0, 1 and the negative number starts with 1, 0. Okay, so going back to our previous example, what we had seen about the number 1, okay, represented in 8-bit. So which is the normalized number? So if you go back, the normalized number, what you can see here, which starts with 0, 1, is this number. This is your normalized number. Why? Because this number starts with 0, 1. Okay. So let's take an example and run through and see how we can have a normalized floating point binary. So let's take an example, 6.5 in denary. Okay, let's convert into a normalized form. What we do is first write that on a standard fixed point binary. Use the fixed point binary number line and represent 6.5. So normally 8-bit binary line, we'll just write it 16. So let's plot on it. So your first is 0, the MSB is because it's a positive number. 0 is 6.5, so you have 1 and a 2. 0 is 0.5, so it's a half, so we have 1, we have 0, 0. So now let's look at 4 plus 2 plus 0.5 is equal to 6.5. So we have the number 6.5, which is normal. Next, move the binary point to sit between the first 0 and 1. Why first 0 and 1? Because it's a positive number. Your binary point is on a fixed line is here. So which is your first number where you have to place it? So we have to move it from here, 1, 2 and 3. Why here? Because it's 0 and 1, so positive number. So you moved how many places? 3 places to the left. So moved 3 places to left. That means my exponent is 3. Exponent is 3. Right? So let's make your Mantissa exponent. So let's draw Mantissa exponent. It's a 3 exponent and 5 is your number. So let's do that. So it starts with -1. Okay, so the number what we have to transfer from here to here. So let's start with 0, 1, 1, 0, 1. So this is what our number is, right? And here your number is 3. So your positive number 0, 1, 1, 2 and 1, 3. Okay, so this is what we got it. So what is the next stage what you have to do? The next thing what you have to do is you have to have 3, right? So your point is here. We are moving 3 places to the right. Why? Because we moved 3 places to the left. So you move 3 places to the right. 1, 2, 3. Correct? So let's calculate that, putting that on your normal number line. This is your 8-bit number line. Okay, so let's plot it back. 1 1 0 1, right? This is where we brought it 1 to 3, so 3 places. Let's put it 0. Now it is, this is 4, this is 2, this is 0.5 is equal to 6.5. So we got back our number 6.5, right? So other example what we are looking at is 2.5 is your denary value for base 10, right? So convert this into normalized floating point, correct? So what do? Same thing what we did before. Plot it on a 8-bit number line. So it is minus 16, then okay, so 2.5 to store, so 2, so 1 and 0.5. Okay, we had around 6.5, so let's change this to 2.25. Okay, instead of 2.5, let's change it to 2.25, because 6.5 and 2.5 is hardly a difference, so let's take 2.25. So let's have 1 here. Okay, it's a quarter, so let's rest other populate with 0. Your MSB is 0 because it's a positive number. So we have now 2.25 stored, right? 2 and 0.25. So that becomes 2.25. Okay. Now, what's the next thing we have done it? I hope you remember what we did in the previous one. Next, we have to move the binary point. Now, the binary fixed point is here, right? So we have to a normalized positive number. Normalized positive number starts with 0 1. So where is the first 0 1? What we can see is here, right? So what do we do it? Now we move this 1 2, right? We move the decimal point here. So how many places have we moved? We have places moved is 2 places to left. Okay, so your exponent is 2 because you moved 2 places to the left. So let's put that into your Mantissa exponent. Your exponent is 2, correct? So 0 1 0. Plot the same number what you have here. Okay, so the number is 0 1 0 0 1, correct? So how many places we had moved? So look at the last step what we have to do. Now we have to move 2 places. The decimal point what is here, we have to move 2 places to the right. Why? Because we moved 2 places to the left. So 1 2, right? The point came here. So what's the number on the number line? If you look at the same number line, so we have 0 0 0 1 0 0 1, correct, as before. So 2 plus 0.25 is equal to 2.25. 5. So easy. Okay, we have done two positive numbers, so let's take one negative number and let's see how does it work, or what is the trick to get it done. Okay, so let's minus 2.5 in a normalized form. Okay, best thing to do is taking minus 2.5 in a normalized floating point. Is the easy way is to write 2.5 in a positive fixed point number line. So in a fixed point number line, it's very simple to do it in a fixed point number line. So let's do on the fixed point number line. So it's 2.5 positive, so it's 1.5, it becomes 2.5. Let's populate others with 0, and we said it's fixed point number line, so your 5 and 3 8-bit, so fixed point number line comes here. So now this is what we have got is 2 and 0.5 is equal to 2.5 is a positive thing. Now how do we change this to a negative? So remember one rule here, which is very easy to do that instead of doing a calculations and all. Start on the right hand side with the least significant bit. So your least significant bit is here. This is the least significant. So from right side, start moving towards left side. And what do we do? Copy each bit. Okay, I'll just write it down. Copy each bit. From which side? From left side as it appears. Left as it appears. Up to and, that is including the first one. Okay, the first one you encounter. So the first one we have encountered is here, right? If you can see there, marked with blue. So this is the first one what we have encountered here. After you do that, after the one is encountered, first copied, and okay, the second is swap after everything. Swap all zeros to 1 and 1 to zeros, right? So how do you do that? So this is what we have it, right? So let's write the same number line. 16. Yeah. So it starts from the left hand side. So it took 0, 0, 1. Now the first one has been encountered. So now once the first one is encountered, we swap all the other numbers. So next is 0, 0 becomes 1, 1 becomes 0, then 1, 1, 1, because all others are 0. So 0 has become 1 and 1 has become 0. Now your fixed point binary was here, correct? I'll mark it as red. This was here. Now we have to normalize the negative number. So what is the rule of normalized negative number? The number should start with 1 and 0, right? So where is the 1 and 0? What we have first here is your binary number has to shift 1 and 2. Why? Because this is the first 1 and 0 what we have it, correct? So we have moved how many places? We have moved 2 places to the left. If you have moved 2 places to the left, it means your exponent is 2, right? So because you moved to the left, so it's a positive number, so plus 2. So let's plot it back onto your Mantissa and exponent and see what are we getting it. I'll keep it till here, so you do it. Let's take your Mantissa 5 and 3, so it is minus 1 half 1 of your point is always here. So let's plot from your number line to here. Starts with 1 0 1 1 0, correct? Because now we have moved 2 places to the left, that is what we have it here. We have to move now 2 places to the right. Now how do you move 2 places to the right? So I'll take a blue color. 1 2. So your decimal point has come here. So let's put the same decimal point back onto your number line what we have before. Too many blue colors, so let's take a red color. Now plot it back, that number. So what we have here is, right, because it has moved here, so you have 1 0 1 1 0, then rest just put 0, correct? Now what do you have? Minus 4, then 1, and 0.5, add it up, it becomes minus 2.5. So you have the normal binary weightage number, which gives us minus 2.5. Okay, let's take another number. I'm giving the number and I will pause and you will make the solutions. The rule, first put it on a fixed point binary. So your fixed point binary is 0.25 will come here, rest will be all 0. Okay. So we put the minus 0.25 has been stored as 0.25 positive number right now. Okay. Now what we do is swap and copy and swap this number from left hand side. So how do you do that? I'm not writing the 16 again. I'm just writing the only the bottom part. So it starts from 0 1. Now so this is your copy. Okay, and this will be your swap from here to here. So 0 0 0, so it becomes 1 1 1 1 1 1. So all have become 1. Now you have to move your fixed point binary, which is here, right? The fixed point binary is here. Now we have to move to the first 1 and 0 because it's a negative number. So your first 1 and 0 is which side? It's on the right hand side. So you move 2 places to the right. two places to right. Why? Because it's a negative number. Okay. To get the normalized, it's 1 and 0 if you remember. 1 and 0, correct? Now, what do we do? As we have moved two places to the right, so let's populate our Mantissa. So it's a negative number because moved to the right, so it is, so your exponent will be negative. So it is 1, 1, 0. Minus 4, minus 2, minus 4 plus minus 2 is equal to minus 2. Correct? So let's look at your number line, the the final stage. So your number line is 8-bit is minus 16, 8, 4. So let's populate it. 0, 1, 1, 1, 1, 1, 1. It's a negative number. This is where your, what does it say? We have to so let's put it to Mantissa. Referring to the same, right? So we have 1, 0, 0, 0, 0. Because you have moved to the two places to the left, so you have to move two places to the right. So we can't shift the entire number line. We can't shift this side, correct? We can't shift this side. Why? Because our number line is fixed here. So what do? We just move the number line. Instead of moving the decimal point, we move the number line. So let's say decimal point remain fixed here and we move the number line. So we have, okay, so we move two places. So it will be 1, 0, 0, 0, 0, 0. Because you move two places, right? So let's populate this to 0, 0. Should we populate this to 0, 0? If I populate here with 0, what it becomes? A positive number, and we are looking at a negative. So when it's a negative number, we backfill it as ones, not zeros. What we do it, we backfill as ones, not 0. So your number line is 1, 1, 1, 0, 0, 0, 0, 0. Okay, so let's look at it. Minus 1 plus 0.5 plus 0.25 is equal to minus 0.25. So we got a number. Great. If you got the same answer, very good. Let's have a recap of whatever we did it. Okay. We introduced the concept of floating point binary and normalized numbers. Okay. So we learned that instead of having floating point binary, we understood what is a fixed point binary and what is the restrictions about the fixed point binary numbers. Then we saw how we can solve with floating point binary. But even after having the floating point binary, we were looking at more precision or of data. So what we looked at was the normalized form of data. Okay, so we looked at the normalized form of data, which gives you the highest degree of precision. So please remember this, that normalized numbers gives highest degree of precision. So let's remember few things from here, from the entire video what we have done it. The Mantissa and exponents are stored in 2's complements. Okay, your Mantissa and exponents are stored in 2's complement. Okay, this is the first point. The binary point always starts from the first two digits. So your binary point starts from where? Now if this is your number, it always starts from this side. Okay, it's always between the first two numbers. The positive number starts with 0 1 and the negative number starts with 1 0. The Mantissa is the actual number. Okay, so your Mantissa is the actual number, and your exponent is the position we have to move the binary point. Okay, how many position you have to move, which will be stored in the exponent form. The positive exponents move the binary number to the right, and the negative moves to the left. So remember that. For the time being, I'm not giving the solutions. You can find out. So take the numbers 3.5, convert into 6.75 and 2.75. These are the three examples I wanted to solve to a normalized floating point, normalized floating point binary. Thank you. I hope you understood the topic. Bye for now.